So we are finally going to learn how to do the thing today. I'm guessing your x-axis is labeled there. For some reason, my x and y-axis aren't labeled. Oh, they're not. That's in both an issue on both. Okay. But they are just counting by ones. There's nothing special about that, I don't believe. Yeah. We're going to have to deal with it. We're going to count them by ones. We'll have to see what our variable represents and see if it makes sense to count by ones. I need to answer this question for myself as to whether that's right or not. Just never getting started. All right, this would be E4. Probably have to go into the old folder. It's probably not E4 in the old folder. It's probably some other number that I can't find. Let's see. Is it E4? It's not E4. This is going to be a different one because I changed all the numbers. Might be E6. We're about to find out. Nope. Word's got to open even though it's already open. Word on the street was you were going to Philly.
I'm going after school.
Okay.
I was in guidance week last week.
Okay. So I have to mark you present. Okay. So here we are, E4. I verified that these are supposed to be counting by ones, despite the fact that sometimes when I change things to PDF, that disappears, and I don't know why. Usually it doesn't happen on your paper. This time it did. This graph represents rain being collected in a cylindrical bucket. Not that that matters. Feels like a related rates problem. The graph to the right shows the function r of t, which models the rate at which the height of the water in the bucket is increasing. That is measured in centimeters per hour, where t equals 0 represents noon. R of t is a piecewise function consisting of a line and a quarter circle. Letter A says, what is the relationship between h of t and r of t? So h is the height, and r, I don't want to give too much away, is what it says up there. What are h of t and r of t? There you go. Yep, it is the derivative. What is the derivative? It is the derivative is a terrible sentence because it's got too many pronouns in it. Perfect. R of t equals h prime of t. Know your function. Now that we're going into integrals, know your function really, really comes into play here. If there are 50 gallons in the bucket at 2 o'clock p.m., write and solve an integral to determine the height of the water in the bucket at 6 p.m. And by solve, it means we're just going to take the area under the curve. So this kind of brings out what our integral does. What does our integral help us solve? So 2 p.m. is t equals 2. And we want to know 6 p.m., so we want to know here. So if we find the area under the curve, that will tell us how the height of that barrel has changed in those 4 hours between 2 o'clock and 6 o'clock. So if I write the integral from 2 to 6 of, what's my function that's graphed? R of t, dt. That part is going to equal the area of that shape that we have there. And to find that the area of that shape, I can kind of do it in a couple ways. I could think of the area from 2 to 4 as a trapezoid, but probably a little bit simpler. I can think of it as a rectangle with a triangle on top of it. So the part that I have in blue, what's the area there? So the combined area between the rectangle and the triangle. 3. Yeah. There's 2 squares, count them, in the rectangle. And then the triangle is a 2 by 1 triangle. Half base times height is 1. It is also exactly half the size of the rectangle. Another reason why it's 1. So that's going to give us 3 there. Okay. There's a reason why I left a space. So then I need the area of the quarter circle. Despite the fact that quarter circles and half circles don't usually. Sure. Are they by name? All right. You just want to hand me them and I'll forget to give them to them? Perfect. I love it. All right. So despite the fact that half circles and quarter circles aren't graphs of the way real things work in the real world, they do tend to show up on AP questions. So we have a quarter circle with a radius of 2. Its area is, that would be the area of the circle, right? The area of the circle would be pi r squared, but it would be 1/4 pi r squared. So we end up with just pi, right? 1/4 pi times 2 squared, and the 2 squared and the 4 will cancel out. So it's going to be basically 3 plus pi. Okay. So that integral does equal 3 plus pi. I definitely have a mislabel here. Let's change this, and let's make this say 10 inches. I don't know if I even caught this. Yeah.
Oh, 'cause it's the height.
Right. Our function is inches, not gallons. So, yeah, that great that there are 50 gallons, but that doesn't help us. And just to keep it in line with, and actually not even 10 inches, I think it's 10 centimeters. All right. Today is going awesome. Like this is, you missed how awesome it went. The height of the water? I'm all right with height of the water. Yeah. But it wouldn't be the height of the centimeters. You're not measuring how tall the centimeters are. Okay. I'll stick with that. So this is the key to integrals, though, despite everything else of the nonsense that's going on here. When you get the 3 plus pi, which is about 6, right? That is just telling you how much the increase is. Since it's positive, it's an increase. So to figure out how much water there actually is in the bucket, we have to start with 10 plus, and we need to keep that 10 plus over here on the right side. So, in the end, the answer is 13 plus pi, which is a weird number, but it is the answer to this question based on the way it's written. Okay. All right. Now, that idea from letter B is something we're going to revisit in future problems. But for right now, this is kind of developing where this fundamental theorem of calculus comes from. It feels like, I think, a little bit random that we kind of do it in this way, but this really is hopefully going to show you where it comes from. So we want to write the equation we just wrote in terms of h of 2 and h of 6. So keep in mind that in that initial sentence that I fixed, the connection here between 2 p.m. and 10 centimeters was telling us that h of 2 equals 10. Because 2 o'clock would be 2 hours after noon. Set that one up so that would be just easy to see. So we want to rewrite the equation we wrote for part B in terms of the integral, h of 2 and h of 6, and solve for the integral. Yeah, go for it. So we had, the thing we wrote as our integral was 10 plus the integral from 2 to 6 of r of t dt. And that ended up equaling 13 plus pi. I just said earlier that that 10 comes from the h of 2. And 13 plus pi is the answer to how much water is in the bucket after 6 hours, right? So that's actually h of 6. It's solved for h of 6, but we want to solve it for the integral. So if I solve for the integral there, I will end up with the integral from 2 to 6. I'll write it a little bit nicer. R of t dt. It does equal the h of 6 minus the h of 2. think about what h of 6 minus h of 2 would tell you. If I knew the height of the water in the barrel at t equals 6, and I subtracted the height of the water in the barrel after t equals 2, what am I finding out when I subtract those two amounts? Not average, no. The change, just the change. This is the change. The bathroom? Bathroom Wawa? Hallway Wawa. They're weird. All right, yeah. So basically, yeah, I know the height at 6. I know the height at 2. When you subtract them, you figure out how much the change is between h of 6 and h of 2. So literally, what this is saying, which is the fundamental theorem of calculus, this is what an integral is. It actually tells us two things. The integral represents the change from the lower limit to the upper limit. Okay? How much change happened from the lower limit to the upper limit, and we find that by integrating the rate. And that is the fundamental theorem of calculus. It makes sense in context, but it's also going to be how we solve integrals, and that's what's so important. So it does say discuss the meaning of this new equation. The integral is the amount of change from the lower limit to the upper limit. Not average rate of change, but the actual change that happened. It's just backwards from what we did in derivatives. When you were finding average rate of change, that h of 6 minus h of 2 was your numerator. You were figuring out how much changed in the time that elapsed, and then you were dividing by how much time had passed to actually get a rate. Now we have the rate, and we're reversing backwards to get the change. Okay. So here is the fundamental theorem of calculus. You are given a function. That function is f of x. If it's a context problem, that f of x represents the rate of something. If it's just a problem on a worksheet to solve, it's the function you're working with. It's on the interval, it's continuous, and it's on the interval from a and b. Then you can figure out the integral by taking and subtracting, by plugging your lower limit and your upper limit into something and then subtracting. But the key is that something is the antiderivative of f of x. So that's a new word. Basically, if I took this function and took its derivative, that would be called the derivative. But if I took this function and said, hey, what other function gives me f of x as the derivative? That's an antiderivative, right? So it's just the process we're doing in reverse. So let's take a look at first antiderivatives, and then once we get those, we will solve some problems.
Wait, how are you able to find which exact function gives you that derivative?
You can't. So I'm always going to say an antiderivative, and it turns out it doesn't matter which one you use. That's the nice part about it. All right. So, but that, I mean, honestly, Franklin's question just leads to exactly what we're talking about. This first sentence kind of said what I just said. On to the second sentence, when we work our way backwards, you have a function and you want to know what gives you it as a derivative. We call it an antiderivative. And, not the, because here's three functions. X squared minus 100, x squared plus e to the pi, which is just a number, right? There's no function in that one. I picked a weird one. They all have the same derivative. F prime of x equals 2x. So if we think the other way and I want an antiderivative, I have to say an antiderivative because I could pick one of these or really any x squared plus a number. But honestly, if we just need an antiderivative, why be complicated about it? Why do minus 100? Why do plus e to the pi? The antiderivative that we generally pick is the one that doesn't have any extra numbers after it. Okay. So basically, what we're going to kind of do in this next section is think about working in reverse. First, we'll start with the power rule. We'll kind of do it in the order we always did it in taking a derivative. And then we'll reverse that process for taking an antiderivative, finding an antiderivative. Okay. So if I give you a generic function, which is just x to a power, x a variable to n some number, the derivative is, what's the coefficient? N. And what's the new exponent? N minus 1. So we multiply by the old power, and then we subtract 1 from the exponent. All righty. Now, we need something that gives us x to the n as its derivative. So we really need kind of two things here. We need to add 1 to the power. Divide by the new power, correct. Yeah, we are going to end up needing to add 1 to the exponent and then divide by that new exponent or new power. So we kind of do the process in reverse. We add 1 to the exponent. Step 2 becomes step 1. Step 1 becomes step 2. Divide by the new power. So x to the n becomes 1 over n plus 1, x to the n plus 1. Which can also be written, you can slide that x into the numerator. All right. Hey, let's find some antiderivatives. Find an antiderivative, f of x, given a function which we're thinking as something that already is a derivative. So f of x equals x to the 4th. An antiderivative f of x is x to the 5th over 5. Yep, you added twice. We only add once. We followed the two rules. We added 1 to the exponent. 4 went to 5. We divided by that new exponent, 5. One of the things when I'm teaching algebra 1 or even algebra 2, whenever we're talking about factoring, this thing that leaves my mouth that nobody ever listens to is when you factor something, right? When you take a polynomial and you turn it into x plus 3x minus 2, you can always reverse that process backwards and make sure it works out. Question? No. So an integral, if I wanted a symbol, I'd use an integral. There's a little bit more to that. So I'm just using the word antiderivative in a capital F, which is common, but it's not like if I see a little f and a big F, that's not a guarantee that it's an antiderivative. If I were to go work in reverse, if I take the derivative of my antiderivative, I should be back to where I started from. So go back to what you would do if you would take a derivative here. You would multiply by the old power, which is 5. So you'd have 5x, drop the power by 1 over 5. Did I get back to where I started? Yep. So yeah. So, that's your check. I mean, it's a process that you can reverse, do in reverse. We're reversing a process. So if you do it in what we know and love is finding a derivative, you should get back to where you started from. Okay? So opposite sort of order. First, you change the exponent, then you divide. So because we're reversing, so we do the steps backwards. So number 2, we've got a sum and difference here, and this works just like it does when we're taking derivatives. I can do it term by term because it's addition and subtraction. The things that work nice for derivatives work nice for integrals. Most things don't work nice, but addition and subtraction does. So first one, 4x cubed. So f prime. That's correct. That one is going to be x to the 4th because we increase the power by 1 and then we divide by 4, which cancels the 4 that's already there. Oh, sorry, there should be no prime there. And actually, I want to leave space because I want to rewrite the parts. This, I'm happy here because here I was actually finding a derivative. But so this is my capital F. This is my derivative, which gets me back to where I started from, little f. All right. So we just said that our first term is x to the fourth, 6x cubed. We should rewrite that as, right. Okay, so let's, before we start. No. So two things. Add 1 to the exponent. Our new exponent is -2 plus 6x to the -2 divide by -2 gives us 3x to the -2 or 3 over x squared. Did you say that? I thought I heard a 7 out of you, and that's why okay. Maybe I just misheard. Yeah, 3x to the -2. Yes, should that I'll turn negative. Thank you. Yep. Okay. We'll write this. We'll clean it up in one more line. So, but let's deal with the 1. Right. So when you take a derivative, constants go away, but when you take an antiderivative, they appear, right? Like -1, what gives us a derivative of -1? -x. So constants do not go away, so we end up with -x. So we end up with a much cleaned up version, x to the fourth minus 3 over x squared minus x. And we have found an antiderivative. If I went backwards, the two on the end should be obvious. The derivative of the first term, x to the fourth, is 4x cubed, which is what we wanted. The derivative of the last term is -1. The derivative of -3x squared, that 3 would get multiplied by the old exponent, -2, giving us our +6, and taking a derivative drops a -2 down to -3. Okay. All righty. And now for a fun one. F of x equals x to the 1/2 minus 4x to the. We're rewriting. We're not taking an integral yet. -1/2. Yep. Also, that's another thing that I see, especially now that we hit derivatives. Know what you're doing and when you're doing it. When you're rewriting, you're rewriting. So we're not changing anything. If all you've done is rewritten, you haven't taken the antiderivative yet, which is another thing. Sometimes people make the change and then never actually take the antiderivative. Okay, so we're going to follow the rules. We're going to add 1 to the exponent and divide by the new exponent to write our f of x, which does not have a prime next to it. So, new exponent first. X to the 1/2 is exponent first. I just want the exponent. X to the 3 over 2. We haven't done the coefficient yet, but we know we're going to be x to the 3/2. Now we've got to, flip it. Divide by 3/2. So we're going to, because it's a fraction, reciprocal, 2/3 x to the 3/2. All right. All right. So we have a -4. That's a coefficient. We can leave that alone. X to the -1/2. Start with the exponent. The new exponent is +1/2. Yep. And I've got to multiply by 2. Because I should have said I'm dividing by 1/2, which means I multiply by 2. Okay. So 2 is just the reciprocal of 1/2. So this antiderivative is 2/3 x to the 3/2 minus 8x to the 1/2. And I can even write that as 2/3 the square root, root types never change, of x cubed minus 8 square root of x. And I wrote an equal instead of a minus. Which part? I did write an extra 2 that I didn't need. Oop. It wasn't wrong, but it was not necessary. Any objections? There was a, wait, that's not right, but what's not right?
I'm just being
Okay, no, I think it's right. All right. Okay, so you know those must-knows that you love from test fame? Yeah, Joey's like, these are the best things in the world. Yeah, they're gonna just show up backwards. I'm gonna be giving you the answers, and you're going to be giving me the problems. You know, because we're doing antiderivatives now.
just for everything, memorizing it.
So, what function gives us positive sine x, negative cosine x? Nice. Oh boy. Which function gives us cosine x, sine x? So now we have a reverse association here with our, not a reverse association, but it's backwards. When you're finding antiderivatives, sine gives you the negative result, cosine gives you the positive result. It makes sense. Hey, here's the freebie. What function gives you e to the x? Yes. Yeah, and then this one. Now, here's the one that's not going to match perfectly. The antiderivative of 1 over x. What gives us 1 over x? ln x. But the antiderivative that we're going to use is ln of the absolute value of x. Yep. Yes, and then that is why there is a box equal in size to that right there with the y, absolute value of x. So why? Because the ln, the function that we just said is the antiderivative. ln of x, it's not, is defined this way. If x is greater than 0, because the one number you can't plug into this thing is 0, you just take the ln of x as normal, correct? All right. If x is less than 0, then you don't do ln of x because that you're putting a negative number in it. You do ln of negative x because that's what the absolute value is, right? It really is just the piecewise definition of absolute value of x, but that x is thrown in as an argument. Let's take the derivative of this without writing it all down. The lower piece, the derivative of ln of x is 1 over x. What's the derivative of, I'll change colors for this. What's the derivative of ln of negative x? No. Right. We need to use the linear chain rule here. So the argument is negative x. So the thing that goes in the denominator is negative x. The linear chain rule says we need to multiply the whole thing by negative 1. So we end up with negative 1 over negative x, which is 1 over x. So that means that no matter which piece you're in, the left piece that's less than 0 or the right piece that's greater than 0, the derivative of this piecewise function, ln of absolute value of x, is 1 over x regardless. And obviously, because of both functions, 0 is just not in the domain of the function or the derivative. But anywhere that you have a valid domain number, anywhere that it isn't 0, if you took the derivative would be 1 over x. So we just expand the function when we go in antiderivative terms because this allows us to do more with it. We can plug negative values into both our function and our antiderivative, which we wouldn't have been able to do. We'd have a problem if I had asked you to find an antiderivative and then evaluate it at x equals negative 3 if our antiderivative was just ln x. So we are matching domains here. The domain of 1 over x is everything but 0. The domain of our antiderivative is also everything but 0. So a little bit of a strange one to remember. Oh, the linear chain rule comes back. Right. So we have to account for the linear chain rule when we're taking antiderivatives, but we're reversing the process. So in our forward process, if I was taking the derivative and my argument was 3x, I would have to multiply by an additional 3. when I'm going backwards, I've got to divide that 3 out. We'll look at it, we'll look at it in both directions. Once we take the antiderivative, we'll verify that this is the thing that we have to do. Okay, so if f of x is the cosine of 3x, then the antiderivative there, start with the function itself, then worry about the coefficient later. We're going to use sine 3x. And then since we're doing antiderivatives, the linear chain rule will say divide by 3. So 1/3 sine 3x. And again, if I was trying to reverse this process, if I wanted to find capital F prime, I better get my original function. The derivative of sine is cosine. Arguments never change. Linear chain rule tells me to multiply by 3. So I end up with 3/3 cosine 3x. Honestly, for antiderivatives, this is the reason why I introduced the linear chain rule back in derivatives. Because I want to be able to reverse that process without having to do 3 times the work, which is what we'll have to do later on for reversing the chain rule itself. But the linear chain rule is just dividing by a number. Okay. All right. Let's take a look at the next one. F of x equals e to the x over 2. What's my coefficient in front of x there? 1/2, right? So this is the same as saying e to the 1/2 x. So I take my antiderivative as normal, a thing we've known how to do for 15 minutes now. Right, so it's going to be e to the, I don't know why I left all that space. It's still going to be e to the 1/2 x. Arguments never change. The derivative of e to the x is e to the x. But now it would be 2 because we have to divide by 1/2. So that's going to be 2 e to the 1/2 x. Again, thinking the forward process, if I gave you capital F and asked you to take the derivative, you would say, well, e to the x is e to the x, but man, since it's linear chain rule, I have to multiply that 2 by the 1/2 and cancel it out. Okay. All right. Same thing in number 3. We are going to use the power rule, but we have a linear argument, right? So we've got to do our new power rule, and in the end, we've got to divide by, not 2x minus 5. Oh, you're right, but sorry. In the end, though, I was thinking about linear chain rule. You're right. Okay, let's do both. So let's do power rule first. I went too fast there. No worries. Okay, so we're going to increase the power. So arguments never change. We have 2x minus 5 to the 7th power. We've got to divide by 7. But the linear chain rule says we also have to, if we were taking a derivative, we'd multiply by 2, divide by 2. So the whole thing gets multiplied by 1/2. Yep. So it is 2x minus 5 to the 7th power over 14. So the new power, this is the same thing that happens in the regular chain rule. The power and the chain rule part interact, but in an antiderivative, they interact in the denominator. So I needed to divide by 7 from the power rule, and I needed to divide by 2 from the linear chain rule. So I ended up with 2 times 7 in the denominator. All right, let's try number 4. We'll rewrite it. We have 6 minus 5x to the 1/2 power. So when we find our capital F of x, do power rule first. Our new exponent is 3 over 2. So we've got 6 minus 5x to the 3 over 2. So we need to either divide by that 3/2 or multiply by 2/3. So maybe I'll show it that way. I'm going to rewrite that just in line, rather than writing it as a fraction. So we multiply by 2/3. And then the linear chain rule tells us we need to multiply by Negative 1/5, correct. Making our final answer negative 2/15. Arguments never change. 6 minus 5x to the 3/2. Okay, so here's where we're at. We kind of looked at two very separate things. The beginning of class was to come up with the fundamental theorem of calculus, which, as far as the amount of ink it takes, is not very much. You just need to, if you need to find an integral, you need to plug those two limits into an antiderivative. What's an antiderivative? That's what we spent the second half looking at. We learned almost all the simple rules. There's ones for tangent, secant, all that stuff, but they are just the reverse of our other ones. So what we'll have to do, the two steps that we're going to do when we go over the next section on Monday, is we will first find an antiderivative, then we will plug both numbers into that antiderivative and subtract. So we're putting a couple pieces together on this one. What I want you to do in the last 10 minutes of class is look at numbers 1 through 6 and find those antiderivatives. So